Hello, my name is Guilherme de Azevedo and I'll be talking about generating magic with constraint programming. A central problem in the performing arts of magic concerns designing new effects which are easy to execute while complex enough so volunteers cannot figure them out easily. Magicians traditionally use trial and error procedures that take time and are limited to their experiences. They use heuristics, but heuristics might not work under different circumstances. Mathematically inclined magicians publish proofs based on number and set theory, or even properties on the Brueggemann sequences, which directly translate to a deck of cards. Programmers create closed source code exploring possibilities on memorized stacked decks. But even after the effects of those creators are published, they might not be replicated by magicians who perform them in other languages or countries, since many card effects use characteristics from their own cultures. One such example is the language bias, as in the value and suit names in English. Some effects even use double meanings of words such as jacks or clubs. In Portuguese or other languages, it just doesn't apply. Memorized decks such as the Arneson stack are built around card spelling characteristics from the English language. Jack has 4 letters in English, but valete has 6 in Portuguese. Moreover, nationality bias diminishes the reach of magical effects beyond the creator's cultural bubble. Poker is a central theme in many magical effects, but is not related to Brazil's national card game identity. Even the so-called traditional deck of cards is only traditional in an European-centric bubble. Therefore, designing effects based on the properties of a deck of cards is traditionally a time-consuming process, limited by the cultural aspects, biases, and experience of a creator. The type of magic we will discuss here today is called mentalism. In it, a volunteer makes some choices, and the magician or mentalist reveals to have predicted it beforehand. Mathematics and mentalism walk side by side in many approaches, some of which involve forcing a result. Let's do some mentalism. Choose a positive integer with 2 digits. Add 6. Multiply by 2. Add the original number. Now divide by 3. Subtract the original number. Let me try to read your minds. You got 4. This is a straightforward definition of a force. I forced you the number 4. And you probably figured out why. Now let me show you one spelling effect that we want to improve. So let's take this deck of cards, give it a quick shuffle, followed by a cut, and I'll ask you to say stop whenever you want. Here, which one do you want? This one here? You sure? Okay. Now you chose the 4 of diamonds. Let's take a look, because I prepared something beforehand. You can see the 4 of diamonds. How do we spell it? F-O-U-R. That's the 4. Of diamonds. And here we have the 4 of diamonds. While the volunteer made a free choice, the performer controlled its result by giving them no other option. The magician has also placed the 4 of diamonds at the exact required position. And that's how you do this force. The problem with forces is that the audience might smell them. When they suspect they did not really have a free choice, the magical effect is over. This motivates us to ask whether there are methods to provide free choices to volunteers while retaining control on the final result of the effect. But how can we structure this idea? First, the selections made by the volunteer can be understood as parameters to the magic effect. Parameters can be randomly chosen from their own parameter space. In the example given, there is one choice from a 1 to 52 discrete space, making it a one-dimensional parameter magic effect. And so we refine our question. Do magical methods exist that allow volunteers to make n random choices over an n-dimensional parameter space while handling them real control over the card sequence and yet allow the magician to force the results? This brings us to our effect, freedom of spelling. This is the resulting effect. The magician shuffles and cuts the deck. The volunteer will say stop to cut the deck into 4 stacks. Stop. Okay, here. Again. Here. Great. Last time. Great. Then the volunteer puts back together as they wish. Yet the magician had predicted the card, one single card. This card is the 7 of spades. Let's spell it. SEVENOF-SPADES. 7 of spades, and here we have the 7 of spades. Because this type of deck of cards has 52 cards, there are 52 factorial possibilities for deck order. And yet we made it to work, correct? Not really. This is the misdirection. The volunteers believed there were 52 factorial possibilities, which, as we will see, was false. When we look at the effect, there are 2 free selection parts. First, there are 3 choices made where the volunteer will cut the deck. 3 choices, which means 3 variables, each one of them from a different parameter space. Then another 3 choices, which is actually a permutation of the numbers 1, 2, 3, 4. This constitutes a 6-dimensional parameter space. Now, can one predetermined single card be there always, no matter the choices of cuts and stack permutation? For example, the 4 of diamonds has 14 letters. If that's the card, can it always be at position 15? 14 plus 1? It's impossible because of the permutation step. Suppose the first stack contains 15 cards, and the last one is the 4 of diamonds. This would imply that if the first stack selected first or second, it would be or not be in the expected position. Hence, with the current modeled effect, we cannot guarantee one single card to be always at the expected position. Now, how can we modify the problem? Is there perhaps one card, each time a different one, at its expected position, that only depends on the set of these 6 parameters? For example, one set of parameters will give the ace of hearts at position 12. Another set of parameters will give the 4 of diamonds at position 15. Let's model our problem. The first cut must occur between the second card and the card at position 49. The second cut must occur between the first cut and 50. The final cut, cut number 3, must occur between the second cut and position 51. Now the sequence is a permutation of the numbers 1, 2, 3, 4. That gives us a total of 2 million possibilities. The path to model our problem was to first create a table of each card name and its length. For example, the ace of spades has length 11, 2 of spades the same, 3 of spades 13, etc. Then we have the cards in its starting order. Let's name the cards from number 1 to number 52. Let's fix one set of parameters. For example, 12, 24, and 41. Now we rebuild with the second set of parameters. Let's suppose 4, 3, 2, 1. For that one specific set of parameters, this is the resulting stack. The cards that ended at position 11 to 16 are 51, 52, 24, 25, 26, and 27. We can now create a constraint that says that any card with 10 letters needs to end at the 11th position, which means it needs to start at position 51. Any of the cards with 11 letters needs to end at position 12, which means starting at position 52, and so on to position 27 for cards with 15 letters. But this would only work with this set of parameters. So we look for all 2 million parameters in the domain and create all constraints that need to be satisfied. A few extra constraints need to be added to guarantee all cards start at positions between 1 and 52, and all cards start at a distinct position. No solution was found using Z3 Solver in less than 24 hours of runtime. We need this to run on any creator's computer. So we remodel the performance and optimize its constraints set. First, all card names in English have length between 10 and 15. Therefore, if different starting parameters end up with the same cards in these positions, the constraint, which is redundant, is removed. Also, although all cuts are possible, during performance this is not true. Magicians know that volunteers do not make their cut on the first few cards, even when given a free choice, as an example. Therefore, limiting the parameter space as follows achieves a similar effect. The first cut is in cards between 7 and 21, the second one between 12 and 26, the third one 25 and 39, and the sequence can be any of the previous ones. In their real lives, magicians can limit those choices by just spreading the cards and saying, now please, which one do you want me to cut at? Oh, this one? That's it. So they don't give the choice for these first few cards, and then they move to 12 and do it again. Finally, we can also make the effect work with either the next card, such as ace, off, spades, and the next card, or it could be the last card, ace, off, spades. We give two choices. After these optimizations were implemented, 2,000 constraints for English are created in under 8 minutes and analyzed, generating one of many sequences of the deck that satisfies the desired properties. The result is called freedom of spelling. Because the code is open source, anyone can run it using a different language, therefore limiting some of the unintentional biases and boundaries a magical effect has due to the identity and experiences of its creator. Generative magic can be explored with other areas of mathematics and computer science. Due to the ongoing pandemic, this performance was mostly executed online so far. This could be performed in real life, such as a restaurant or dinner setting, where a performer can give the piles to the volunteers' hands and allow them to rebuild the deck in any order. They can input the information to their smartphones with, for example, an assistant or voice recognition. Its output can be received with a smartwatch or any kind of tamper. There is future work to model this problem with less clauses and try to optimize the model itself. We are also currently working in variations of this effect and model where it's asked for the language at the end of the effect after all the cuts and the stacks are put back together. Finally, I would like to thank the CP2021 Reviewer Committee for their valuable feedback. Thank you very much. My name is Guilherme de Azevedo.